Right. All right. I think everything's set up now. Hello, welcome back to lecture three. Thanks for sticking in there. I took from the check-in quiz, I got a lot of good responses to the questions that I asked. Especially the what do you want most to take away from this course? Um, I really use that question to guide what things I want to put more emphasis on and what things I can kind of relax a little bit on. Maybe it's not so important because I want to keep this class interesting. I mean, I still need to teach you guys like the most fundamental things about micro, but I can kind of I can kind of cater the material to what you guys find interesting. And if you find the stuff interesting, then it's easier to stay engaged, to stay focused, to do the assignments, rather than if it was something lame and you're kind of just chugging through problems, to get the grade. So at the very least, I'm glad um, everybody can at least find one thing that's interesting about this. Some of the most common things that I had marked down that people wanted to know more about were one was wanting to better understand how people make decisions under uncertainty, something I alluded to in that first lecture. I got a lot of people saying that they want to know a little bit more about game theory and how we can apply this into how we can take this from an economic model, put these things into a game, and how can we depict real life using this type of analysis? So that's one thing we're going to do. Some of you guys said that you want to know more about the math of the models. I got a little bit mixed response, but it's kind of as I had thought that for the most part, you guys are pretty math capable. On average, this is a math capable bunch. Now, again, don't be scared if you're one of the ones that was like, oh, I've done calculus, but it's not my strong suit. Don't worry at all. This course is designed to be taught, and I'm going to teach it using only Calculus 1. So for those that want the analysis, the advanced statistics, maybe I should say analysis and advanced probability, or maybe like just more rigorous math, um, take more classes. Take the higher level classes. This is just intermediate micro. This is just a taste. This is just a small taste of what you can do with these economic models. Um, and then a couple of you mentioned more like political science, political economy type reasons. You want to know about policy analysis, welfare analysis. And then some of you guys wanted to know about more nuanced market structure, like imperfect competition. Why do we have some market failures? Why do we have monopolies? Why are people able to charge higher prices than what would be socially optimal? All of these things can be answered with theory. Now, I take pause right there because I want to put some emphasis, right, really quickly. As exciting as all of these things are, um, the focus of this class and what I'm supposed to teach you guys is just the most fundamental things for micro, for theory in particular. So it's totally cool. Not every economist is a theory economist, and it's okay. Not every pro in this profession likes to do just pure theory, pure what does a consumer do by hand. A lot of them do, and it's very important to have a theory. Because if we don't have a theory, then we have no model to test. We have no way to explain the things that we're seeing in the world. We need math to explain this. Otherwise, it's just gibberish. Otherwise, it's just there's a difference between positive statements and normative statements. This is usually something talked about in the principles of micro stuff. Um, Basically, the gist of it is that positive statements are facts, are what is, whereas normative statements are what should be. Those should type questions. We need theory to get us to positive statements. And if we do the positive statements well enough with theory, only then can we start to make normative statements. But we can't just claim that things should be one way or should be another without defending it with some type of quantitative defense. And usually that comes in the form of a model. So that's a little introduction to just this whole game of econ, this whole the idea of this social science. All right. Because at the end of the day, this is still a science. We need models to do science, and we want to be able to test things. So we need a model to either accept it or reject it. We need to be able to test things, and theory gives us a model, or theory gives us a platform to build models that are testable. All of that to say that we're just now this is more of a theory class, but there are for sure more empirical, more classes with like real world applications. I just at least for right now, I unfortunately won't be the one to teach you that. I'm here to just give you the taste of all the first introduction of the rigorous theory that those other classes use. Because even the empirical stuff, again, they need theories. They need something to test, something to say, okay, here's what the math says. Now let's go look at the real world. What does the data tell us? All right. So you need theory to be able to get to the empirical, to the real world stuff. We need to see how the theory supposes things work, and then let's go to the real world and see how are things actually going down in the real world. And if the theory ain't working so well, then we need to change it. If it does work well, then it says that we got a good theory and we've discovered new laws or what have you. All right. So that's the big picture, what we want to get away, what we want to take away from this class. All right. Now, on to today's topic. Today, we're going further on the behavior of consumers. How do we model consumers' decision making? All right. So we've last in lecture two, in our first real lecture, we introduced the idea of preferences and a budget constraint, the two most fundamental pieces of information, the two most fundamental components of our models, of our economic models. Every single economic model has these two things. You're going to have preferences over some choices, and you're going to face some constraints over what you can choose from. All right. Very realistic setting. All right. Now we're just trying to put this to math. What I'm going to start with is a more intuitive, conceptual explanation. And that's what's going to be this 1.1, the geometry of the consumer's problem. This is going to be our introduction, what we want to do at a very high level. And then once we're cool with that, then we can get into the actual modeling, start the actual modeling stuff. So we're getting into the analysis of the consumer's problem. So let's begin. Oh, and also for this talk, for this lecture, I'm going to be using a little bit from both books. This Landsburg book, this will be for the intuitive part, and then all of the math stuff, I'm going to mostly be teaching from the Perloff book. But I recommend see these chapters, specifically these sections, for more reading on these topics. Okay? Um, all right. I think I had to fix the camera really quickly, at least on my screen. It kind of went a little fuzzy. All right, now let's begin. First, the consumer's problem. All right, specifically the constrained consumer's problem. So as I've said, we've introduced the two fundamental concepts of our economic models, right? Preferences and constraints. Now, how do we use these things? How do we combine the two? How do we combine somebody's preferences with the constraints they face to tell us what are they going to do in a situation, all right? Or we'll refer to it as the optimal choice. So consider the following, all right? Suppose I've given you this. This is your budget constraint, all right? And then I tell you, I'm asking you, is point E optimal? Would this be optimal? If so, why? If not, why not? Well, what do we know? We know that our budget is everything that we can afford, everything that is feasible for us to purchase, to consume, everything, all the above. And so that means we can only consume things on this budget line or underneath it, in the area of the triangle below it. So would E be optimal? Answer there, let me get my color, is going to be no. And why not? I think we know why. Sorry about that. Let's do, there we go. Sorry, one more. And then let's make this just a bit thinner. No. Why not? E is outside of the budget. The budget set. Or you could also, I would accept E is not feasible. So E is not optimal. We wouldn't, as nice as point E would be, we can't get there. It's not within our budget, and so we have to X that one out. What about point D? This one is affordable now, but is this optimal? Again, no. Point D, it is feasible, it is affordable, but it's not on the feasible frontier. It's not on the budget line. If we chose point D, it means we're leaving money in our pocket in this situation. We could have spent more. We could have got more utility by getting more things, but we chose not to. That's what choosing point D represents. And so D is not right. Oh, right. So given that, we know that point E is not feasible. Point D is feasible, but it's interior to our budget constraint. We could have more. So D, we could have more. We're not abiding by the more is better principle. We could spend more, so D is not optimal. E gives us a lot, but it's outside of our budget. It's not feasible, it's not affordable, so we have to mark out E. So we know that A, B, and C are our possible choices. These are on the budget line. These are on the feasible frontier. Now we just need to see which one gives us the highest utility, which one matches with the highest indifference curve. That is how we will be able to tell which one is optimal. All right. So what do I mean by that? What do I mean by that? Well, this should have, let me redraw these points really quickly. So remember we had like point A was right here. Meanwhile, point B was right here. Well, if I were to just draw an indifference curve, maybe something like this right here, we can see that. Let's go ahead and let me do something like this for you guys. Let me draw first and then I will explain. Suppose the indifference curves were given by this red line. If the indifference curves, or if this person's preferences were represented by this indifference curve, then it's easy to see which one is the most optimal. We see that. Of course, all three of these are feasible. We're using all of our budget if we go for A, B, or C. But we see that. Remember, the direction of increasing utility is up and to the right. So yes, we could choose point A, or this person could choose point B, but they would get more utility. They would get to a higher indifference curve if they choose point C. Another thing to notice is that, let's write this down, is that at A and B, these guys, these points, they cross the budget curve, the budget constraint with the, sorry, A and B, they are on the budget constraint. Let me just abbreviate BC. But IC passes through the BC twice. Depending on where you took micro, you will know, you might remember that we don't like that. There's an exact number that we want the indifference curve to pass through or touch the budget curve. We don't want we don't want our indifference curve to touch the budget constraint. We don't want it to touch more than once. Touching the budget constraint once is optimal. Remember also we had a point E. There was a point E. Yes, this point was pretty sweet in that it gave us a higher utility. It gave us a much higher indifference curve. Don't worry about the exact slopes right now. This is just visually. But point E does not touch the BEC. Why? Because it's not feasible. So A and B were not optimal because they pass, if this person has preferences given by this indifference curve, well, at points A and B, the indifference curve that those points lie on passes through the budget constraint or the budget line twice. And we don't want that. Twice is bad. And then we also don't want it to never touch the budget line at all. So that's also bad. So which one is the optimal? Point C. One of the reasons it's optimal is because the indifference curve touches the budget line only once, exactly once. And this is what we want. All right. This is what we want. Mathematically, what does this mean? Mathematically, let me zoom out one sec. What do we see? We remember from Calc 1 that if a curve touches another line, if one function touches another function at exactly one point, there's a phrase for this. We say that the indifference curve is tangent to the budget constraint. There we go. Is tangent to the budget constraint. It touches only once, so it is tangent. That's why point C is optimal. So what do we remember about tangent lines? All right, if we recall from our Calc 1 class, how did we find the line tangent to whatever function? One of the key steps to finding the point at which two functions are tangent to each other, one of the required things is that their slopes must be equal. So at point C, the slope of IC, I'm gonna just underscores or subscript C for the indifference curve that passes through point C. The slope of the indifference curve that passes through C is exactly equal to the slope of the budget curve, of the budget constraint. All right. And we know this is true because this is the very definition of being tangent, of one function being tangent to the other. Mathematically, Remember, the slope of the IC, we call that the MRS, marginal rate of substitution. Meanwhile, the slope of the budget curve is the MRT, the marginal rate of transformation. So what does this mean? Mathematically, and we will see why in a second, but if you remember from the last lecture, that the MRS was the marginal value of X divided by the marginal value of Y. And if these things are tangent, then the MRS is equal to the MRT. And we remember that the MRT is equal to the price ratio, the price of good X divided by the price of good Y. And there is a negative sign here. There's a negative sign, but there's also a negative sign on this side. So they will end up canceling. So long as this ratio is equal to this ratio. The MRS is the marginal value of X divided by the marginal value of Y. And then you take the negative of that, is equal to the price ratio. And if we didn't call it that in last lecture, we call it that now, that this is the price ratio. We care about the ratio more than the exact prices for more mathematical reasons that I don't really need to get into, but that's why we want to refer to it as the ratio. And so it's 100% okay to, once you know these prices, simplify the fraction. All right, simplify the fraction. We want it simple as possible. The ratio matters more than the exact numbers for reasons that I don't need to get into here. So again, intuitively, the MRS is, what does this tell us? One of the things that this tells us is that the marginal value of X is exactly equal to the marginal cost of X. All right. This relates back to what we learned about in principles of econ, principles of micro, about opportunity cost. All right. We want the opportunity cost of, to me, I want how much I value that next unit of X to be exactly equal to how much I need to give up to get that next unit of X. So the marginal value, remember this comes from preferences, utility, or preferences. While this comes from the budget. All right. So what about points A or B? Well, of course, we know that they are on a lower indifference curve than point C. So they're not optimal for that reason. But another thing is that look at point A here. Point A, the slope of this indifference curve is quite steep. So if the slope of the indifference curve is quite steep, is much steeper than the slope of the budget constraint. Let's write this down. So at A, the slope of the indifference curve is greater than the slope of the budget constraint. All right. And remember, we associate the slope of the indifference curve with marginal value. So this is synonymous or analogous to that the marginal value of X at point A is greater than the marginal cost of X at point A because the slope of the indifference curve is greater than the slope of the budget constraint. So if the marginal value of something is greater than the marginal cost it takes to get that something, it's in my best interest to consume more, right? Because I value the thing more than it cost me. So because of this, this means that I could, or I should say, I would be better off consuming more. Would be better off consuming more of good X. And the exact opposite is true for point B. We come back up here to our graph, and at point B, we see that now the slope of the indifference curve is much flatter. Meanwhile, the slope of the budget is now the steep one. So the indifference curve is pretty flat. Meanwhile, the budget looks steeper. So now the slope of the indifference curve is less than the slope of the budget curve. So it's the exact opposite. At point B, slope of IC is less than slope of the budget constraint. This means the exact opposite of what we saw above, that now the marginal value of X, excuse me, is less than the marginal cost of X. And I should consume less. And that's the intuitive explanation of what's going on in this model with the math, with the graph. These are the reasons why. These are just some of the things that we're trying to represent with our economic models. All right. And this is actually a great principle for life. All right. If something is costing you more than the benefit it's bringing you, then you probably shouldn't do that thing. Meanwhile, if you value something at a much higher level than what it costs to you, then it's probably in your best interest to do more of that thing. All right. But that's the intuition of what's going on here in this model, in our basic model of modeling consumer choice. All right. We have a budget and we have our preferences. We have what we like versus what we can afford. And we must always balance the two. This is just one of the ways that an economic model allows us to do that. So that is the high level overview, intuitive conceptual understanding of how we model this consumer's problem. But since this is a higher level class, for Econ 200, that would have been enough. In fact, some of your Econ 200 classes, that might have been what you did, and we call it a day there. But now this is Econ 300. So let's make things a little bit more formal. All right, let's add a little bit of math to it. All right. One of the fundamental assumptions, one of those two fundamental things is that is that the consumer, our economic agent, has preferences. Part of having preferences is that the consumer can compare, can rank different combinations or bundles of goods and decide which one gives them the most benefit, pleasure, or what we will define as utility. That is the unit here in economics, is utility. How much do I value something? And so this gives rise to a utility function. All right. We can summarize a consumer's preferences by assigning a number value, a numerical value to each possible bundle combination of these goods to reflect the consumer's relative ranking of these bundles. How do we do this? We choose some nicely behaved mathematical functions called utility functions. So the utility function is what maps the combination of the goods to a numerical value. And that's how we can compare mathematically. Does the consumer prefer A or does the consumer prefer B? Or is the consumer indifferent? And we need to put units to things. So we will just, but for now, let's just leave it at utils. All right. The unit for utility is a util. How much do I value something is however many utils. So what do I mean by this? So you consider a hypothetical consumer named Liza, who consumes pizza and burritos over the course of a semester. Liza has a utility function, u of z and b, which tells us how much utility she gets from consuming z amounts of pizzas and b amounts of burritos. So instead of now moving away from the abstract, do I prefer this to that? Now we can formalize, concretize things with mathematical functions. All right. So if Liza prefers one bundle to another, then mathematically her utility from the first bundle is going to give her more utility, or is going to be higher than the utility from the second bundle. Quite literally, if bundle one is this, if bundle two is this, then plugging in bundle one into Liza's utility function will give a higher number than if we plugged in this bundle to Liza's utility function. So for example, this is a commonly used one too. A commonly used function for utility is something like a square root function. So suppose that utility is given by this function right here. Z times b, take the square root, or the square root of z times b. So use this function and tell me that supposing that Liza's utility is given by this function, what does she prefer? Does she prefer 16 pizzas, z equals 16, and 9 burritos, burrito equals 9? Or does she prefer 13 of each? So z equals 13 and b equals 13. What does she prefer? If you have an idea of what we're going to do right here, take a second. This should not take you very long, maybe a minute or two at max. Pause this video right here, work it out, and write on your paper what you think she would prefer. All right. Take a few seconds to try this on your own, and then we will see what the optimal is or what the answer is. So if you were able to do that, or you were stuck, still wanted to see a little bit what I mean, let's find out. So utility from the first bundle is, remember, she had 16 and 9. So what is this? It's the square root of 16 times 9. You can punch it in your calculator, or you can recognize that you can do this right here, that you can split the square root since they're just sharing a common exponent. And we know that the square root of 16 is 4, square root of 9 is 3. So 4 times 3 is going to give us 12. Meanwhile, the utility from the second bundle, remember she has 13 of each. This is going to be the square root of 13 times 13. This is easier because they're the same number. So the inside of that is 13 squared. So clearly this just reduces to 13. So what does she prefer? Liza prefers bundle 2. Because bundle 2 gives her a higher utility. I call them 1 and 2, but in the prompt I called them X and Y. All the same conclusion. Liza prefers bundle 2 because bundle 2 gives a higher utility than bundle 1. Okay? It's quite literally just plugging in these numbers to the function and seeing which one evaluates to a higher utility. But that's not the end of the story. That's the very beginning, as a matter of fact. We just needed to see what does a utility function look like. So this is our first example of actually seeing a function behind the indifference curve, because the utility function is directly related to the indifference curve. We will see this in this lecture. As a matter of fact, we're going to see this right now. All right. So now that we're comfortable with the idea of utility and a utility function, in this example that we just worked, we saw that um, this bundle, the first one, gives this level of utility. Meanwhile, this bundle, the second one, gives this level of utility. So these different bundles give different levels of utility. So we should maybe make a note that bundles 1 and 2 lie on different indifference curves. If that's not obvious yet, then we're about to see why that's true. So now that we're comfortable with the idea of utility and utility functions, what do we mean exactly when we're talking about an indifference curve? An indifference curve, remember from the first lecture, is the combination of all points or all the points that represent combinations which give us the same level of utility. So if 2 points are on an indifference curve, then I get the same level of happiness, whether I choose this point or this point, if they're on the same indifference curve. Mathematically, this means that um, all bundles which give us the same output, the same final number. So let me show you what I mean. What I mean by that is that suppose we're working with same utility function, right? Eliza's utility function is given by square root of z times b. Then I can design or I can formulate, let me fix, right? An overbar. This is not statistics. So an overbar in statistics means average. But here, it means a fixed number. So we're going to fix a function to this level. So if we set u bar equal to, for example, say u bar is equal to 2. Then the indifference curve that corresponds to u bar equal to 2 is any bundles of pizza and burritos which give me a utility level of 2. So no matter whether I plug in 1 and 4, 2 and 2, or 4 and 1, they will all give me the same level of utility, 2 utils. This is what is meant by an indifference curve. The combination, it's all different combinations, which when you plug them into a utility function, produce the same level of utility. Visually, rather, remember, this is a multivariable function. So for those of you that have taken multivariable calculus, then you recognize that you can't plot this on a 2D, you must plot this on a 3D graph. And so that's what this looks like. If this is the origin, this increasing in burrito direction, this is increasing in pizza direction. And then this, what would be the vertical direction? This right here is the level of utility. And so that's why we see that as we go from 0 to something, we're getting more and more utility. So visually, this would be a 3D function. This is why it's helpful to think about things in terms of indifference curve, because we recognize that if we're just worried about an indifference curve, we're just worried about one level of this, of like the height component, essentially. So instead of having to look at the whole 3D thing, all right, instead of having to look at this whole 3D box, we can consider just indifference curves. And you can visually, you can see that the indifference curves that we've been seeing are as if I'm looking at this graph from overhead. All right. What I mean by that, this is just a really rough sketch. But if I were to take the 3D graph here on the screen and look on top of it and look down at it, these axes are the same, but I can no longer tell the height axis. I cannot tell where exactly I'm at. I just see the B and the Z axis. And if I were to take a slice, if I were to keep utility fixed, just as was done here, this is what an indifference curve represents. Geometrically, this is how a utility function is working, and geometrically, this is where the indifference curve comes from. Because the utility function is often multivariate, we consider instead indifference curves to reduce the dimensionality of the problem and make things a little bit easier to see. That way, we don't have to work with the 3D. It's a nice, pretty picture, but it's kind of hard to draw and would be a bit um, hard to work with if you're trying to draw this every time in an exam. So instead, we use indifference curves and we flatten a three-dimensional problem down to a two-dimensional problem. All right. So that's a little geometric interpretation of utility and indifference curves. So what are we going to do with this? Let's see. The next thing we want to consider is the notion of marginal utility. Because remember, I mentioned in last lecture and earlier in this lecture that we often care about marginal value of things. Marginal, that word marginal, let's go ahead and lower the page. This word marginal, you guys, now that we're in the grown-up micro class, I'm going to call this one the grown-up class, we should know that marginal should be associated with kind of the same thing as like derivative, the very next step. At the margin means at this point, what does one more do? So when I'm talking about marginal utility, I'm talking about how much utility is gained from one more thing. If I'm talking about maybe, I don't know, what if I'm trying to consider the marginal utility of consuming one more pizza? That's what I'm talking about. All right. So here's an example. Here's an example of what I mean. And you can pause and try this on your own, or you can wait for me to explain. So for example, suppose that we just fix the number of burritos to be 10. So B is 10 and we leave it there. Then how much utility is gained when Liza increases her number of pizzas from Z equals 4 to Z equals 5? If you want to try it on your own, pause the video here now. And if you want to see what I mean, let's go ahead and see how we want to approach this. So remember, utility is given by Z and B, but here we're fixing B equal 10. So B is equal to 10 all of the time. Then we're going to do Z times 10. This is our utility function. If we're saying, hey, we're forcing you to keep yourself at 10 burritos. All right. So with this in mind, let's see. We want to evaluate the effect of increasing her number of pizzas from 4 to 5. We want to see how does the utility change. This is the brute force, you might call it, way of determining marginal utility. So what do? Well, as Z equals 4, maybe actually I want to present it in this way, that utility of Z equal to 4, B equal to 10, and then I want to compare this to Z equal to 5, and then again B equal to 10. All right. The idea of holding the other good fixed is pretty important. We will see why later, but right now it should even be obvious that like trying to change trying to change both goods at the same time makes pinning down this marginal utility pretty complicated. So we just hold one of the goods fixed and we see how does utility change when I just change one of the goods. So here, this would be square root of 4 times 10 or 40. Right here, this would be square root of 5 times 10, right? Which is square root of 50. If you were to plug these things into your calculator, you would find something like square root of 40 is approximately equal to 6.32. We will round it up to 325. Meanwhile, the square root of 50 is approximately equal to oops, 7.071. 071. Thus, what do? You take the difference between the two. Remember, consuming Liza, if she consumed 4 pizzas, she has this much utils. She gets this much utility from 4 pizzas. If she goes for one more pizza, then she has this much utility. She gets this many utils. So, given these two things, the change in utility is going to be the difference between the two. Is going to be square root of 50 minus the square root of 40. And this is roughly equal to 0.74. We're going to round to 3 decimal places. So 0.747 is what I have. So the marginal utility, let's write this down. The marginal utility of the fifth pizza is 0.747 utils. All right. Quite literally, how much does utility change when I consume one more thing? What we just did is exactly what is on the page right here. We compared the extra utility that is gained from consuming that next unit of that good. All right. So the marginal utility, in a more rigorous definition, the marginal utility is the slope of the utility function as we hold the quantity of the other good constant. So if I were to plot the square root function right here, it would look something like this. I think the textbook maybe used a little bit different numbers, so I erased some of the numbers, just so we can get a little bit of a visual of what's going on. So if I were to plot this as a function, like u equals square root of 10z, plot that on a graphing calculator or Desmos. Desmos is a really good tool if you don't use it already. If I were to plot this on a graphing calculator, I'm going to get a shape something like this. And in this way, we can see that the marginal utility is just the slope of the utility function. And this is why it's very helpful to hold the other good fixed. That way I'm able to get a nice function that is represented, that I can graph on a 2-dimensional graph. So if I were to plot that utility function, then I would get a curve like this. And what is the marginal utility of going from 4 to 5? Well, we know that going from 4 to 5 means that I change z by 1. Meanwhile, going from 4 to 5 changes my utility amount by a certain amount, which we just saw was about equal to 0.747. If we were to plot the marginal utility function, taking the derivative of this utility function, which was square root of 10z, just to be a little bit clearer, 10 times z. If we were to plot the function of the derivative of this function, then we get the marginal utility function. If we were to do that, then we would see a curve that looks something like this. Again, coming back to what we mentioned in the last lecture, we design our models in a way such that it has this property of decreasing marginal utility. If I go from 0 to 1, my marginal utility gain is quite drastic. I go from, maybe it's easier to see over here. From here to here, I go from here to here. All right. So I make quite a big jump. Meanwhile, if I already have 4 and I'm going from 4 to 5, then the jump is not nearly as big. This is reflected in this graph of the marginal utility. We see this diminishing marginal utility. Going from 0 to 1 gives us a great big boost. But going from 4 to 5 doesn't give us nearly as big of a boost. The amount of boost is going to be what is the y quantity, the quantity on the y-axis. So from 0 to 1, you get a huge boost. Meanwhile, from 4 to 5, you don't get nearly as big of a boost. All right. And then we see the notion of diminishing marginal utility. That's a bit of graphical explanation of what's going on here. Let's continue. Remember, I connected it to taking the derivative of the function. I said that for a reason because this by hand way of computing marginal utility, it takes a long time and it's just an approximation. Because what did we like to use? What phrase did we like to use in calculus? We like to use the phrase instantaneous rate of change. So I don't care about going from 4 to 5. I want to know that exactly at 4, even if I increase it by 4, if I add 4, like, excuse me. This is what is meant by, in calculus, the instantaneous rate of change. So going from 4 to 5 and analyzing the jump, the change is useful. But what if I want to consider a smaller interval, a smaller interval? So maybe not 4 to 5, but maybe 4 to 4 plus an epsilon amount. Epsilon, for those of you that haven't taken higher level math, it's going to be, when they refer to epsilon, it's going to be a very, 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 very tiny but positive amount. So that's what's kind of, and then if you have taken, I mean, we all taken calculus now, you know that the limit has to do with decreasing the amount of space between where the function's at and where you add to it, all the way until that amount approaches 0, but it doesn't hit 0. That is not so relevant here. Well, maybe it's just a little bit relevant, but that's not the main focus here. I say all of that to say that the way we want to think about marginal utility is in this way. All right. The marginal utility of whatever good, here the marginal utility of the pizza, which we label with z, is simply the derivative of the utility function with respect to z. For example, if u of z comma b is equal to the square root of z times b, then the marginal utility, I will use subscripts to denote derivatives, like I mentioned in the first lecture. But what is this? This is simply du dz. I take the derivative of this function, and this is the marginal utility function. Marginal utility of z as a function. So what would that be? It's easiest to separate the two because this is a square root, because they share a common exponent, right? This is the same thing as this. And by properties of exponents, I can do this. They split apart in this way. Then it's easier to see what the marginal utility is in this way. Because when we take the derivative, if I have a function with 2 variables, but I'm just taking the derivative with respect to one of the variables, then the one that I'm looking at the derivative of, this is what gets like the power rule, the constant, or I'm sorry, the power rule, the quotient rule, whatever, what have you. The other thing, we just treat it as a constant. So if I were to just cover this part up, if I were to say, okay, what is the derivative of square root z? Then you, my brilliant students, you would remember that, oh, that's easy. You would tell me that, oh, this is simply 1 over 2 times the square root of z. And what do we do with the other thing? Well, we just leave it there. All right. And then if we really wanted to clean it up, make things look a little bit prettier, we can recognize that, oh, well, this is simply B, Z on the bottom, and then this is a 1/2. But either is acceptable. All I want to get across is that marginal utility, again, marginal utility is just take the derivative of the utility function with respect to whatever good I care about. All right. And this is just one way in which you can do it. Great. So with that in mind, now this brings us to the notion of the marginal rate of substitution. We remember that this is the slope of the indifference curve. Our indifference curve came from a multivariable function, the utility function. So you can kind of, what might be expected is that I care about the marginal utility of the first good and the marginal utility of the second good. Here, it's Z for pizza and B for burrito. All right. So what we want to do is we want to express, let me go ahead and read this. I think the formal, what I've typed up for you guys here is pretty good. We remember that the marginal rate of substitution is the slope of the indifference curve. All right. We can express this in terms of marginal utilities. So we just saw that if Liza has 10 burritos and 4 pizzas in a semester, and she increases that to 5 pizzas, she gets more utility. And of course, we just saw that extra utility is what we call the marginal utility of the last pizza. You can do the same type exercise for burritos instead of pizza, and we'll get the marginal utility of burritos. All right. We define the marginal rate of substitution as the negative of the ratio of the marginal utilities. All right. For any, if I'm not speaking about pizzas or burritos in general, you take the marginal utility of X divided by the marginal utility of Y and throw a negative sign in there. Because remember, indifference curves are downward sloping. So we need that negative sign in there. And then intuitively, remember, if we have an indifference curve and we go from one point to another, well, we're gaining some utility from consuming more of the one thing, right? If I have an indifference curve and I go from here to here, well, at the first point, I have a lot more of Y than I do X. Meanwhile, at the second point, I have much more X than I do Y. So when we go from one point to another on a indifference curve, we give up some utility from one good in exchange for getting utility from the other good. All right. All of these things together, all of these concepts together form what we refer to as the marginal rate of substitution. More simply, it's simply this right here. Take the derivative, they take the derivatives separately, put them into a fraction, throw a negative sign in front. This is the marginal rate of substitution. And we remember that the marginal rate of substitution, which is related to opportunity cost, is a fundamental measurement which guides how we will model and interpret our consumer's problem. Great. So this brings us to the actual consumer's problem. In fact, the constrained consumer's problem. What did we see above? Remember what we started with at the beginning of this lecture. How did we pick the optimal? How did we pick the optimal point? What we want to consume? We pick the point at which the slope of the IC, the MRS, is equal to the slope of the budget curve, the MRT. This happens. Where this happens is referred to as the tangency point, and how this happens is if this is equal to this. That, with that in mind, then now we formally know what is meant by the optimal choice for our consumer. All right. We know that the optimal bundle for our representative consumer is the one at which the slope of the indifference curve is equal to the slope of the budget constraint. We know that, oh, there should be a negative here. There should be a negative here. All right, so that's a negative sign. The MRS is given by this, and we remember that the MRT is given by this. All right, remember our budget constraint is just a line, and it's a downward sloping line. So these prices are always positive, and so we must throw a negative sign in front. The optimal point is the one at which the MRS is equal to the MRT. This is equal to this. So for most, I make this point here that for most utility functions, for on average, most utility functions, when I'm looking at like, okay, where does this equal this? It will often be it will often be at some point where I'm choosing a combination of these two goods. All right, so that's X, that's Y. For the most part, we will be working with functions, utility functions, and preferences such that the consumer chooses some combination of the two. So they will choose some of good Y and some of good X. They have a little bit of both. But this is not always true. All right. If there is no point, if there's, according to whatever utility function we're working with, if there is no point, feasible point, such that this is equal to this, if I can never find that, then what often ends up being like the outcome is that the consumer will just choose to purchase all of one good or all of the other. If they are never equal, to have a combination of the two, then these things need to be equal. So if there is no way that these things are ever equal, then this clues you in to saying that um, the consumer is going to go with all of one or all of the other. All right. We refer to this as a corner solution. In what I was describing, a corner solution is what I'm marking here in the blue. It means I'm going to either go for all of good X or all of good Y. Here, because I drew the indifference curve like this roughly corresponds to one of those square root indifference curves, roughly. So those are well behaved. Those are the nice ones, and those are the ones we like to play with. And those tend to not give us corner solutions. But other utility functions might. Even these square root things can, but it's just less common. So that's why we like these ones. Other utility functions can have these blue points as optimal. For one example of not even an other function, but maybe instead of having this right here, if instead of something like this, then what if my utility curve was very, very flat? And I mean like super flat. Something like this. Then I find what is the highest utility that I can achieve. I see that no matter where I'm at, I can always get to a higher utility function, higher indifference curve, which yields me more utility. If my indifference curve is very, very flat, then the point at which I get the highest utility is that corner solution. So we can get it with one of those square root type functions, but it has to be in such a way that the curve is very, very flat. And we don't often see that. but it can happen. So that is what's meant by a corner solution. And then you get this point right here, the blue point, which means I would consume all of good Y and zero of good X. All right. Or you could have the reverse. Instead of very flat, maybe it's very, very close to vertical. And it would, the same logic applies. All right. But right now, all we want to cement in our heads for this lecture is the idea, the notion of utility functions, marginal utility, and that the optimality rule is this right here. All right. This is very, very, very important. All right. There's one thing you remember from this econ class at all is that even in lieu of all of this math, all of this derivatives, what does this boil down to? In econ, we need stories. We need stories that tell us about how do people make decisions in real life. We need to explain real life. This is the marginal benefit. This is not exactly the marginal benefit, but this is related to the marginal benefit. And we want to get it to a point where it's equal to the marginal cost. It's not exactly, so maybe I should instead do like a approximately. But what this represents, the whole idea of what I'm trying to represent in my model here is that when this is satisfied, then this is true. When this is satisfied, then this is true. If I can find where does the MRS equal the MRT, then this is the exact point at which the marginal benefit is equal to the marginal cost. One of the key things in economic models is that, yeah, all the math is nice and cool and fancy, especially if you like it. A lot of us economists really like fancy math, but it is utterly useless if it has no real world application. So all the math is cool, but if I can't boil my model down to something that a lay person can understand, somebody who like maybe took a principles class but nothing further, they need to be able to understand the conclusions of the model. If they can't, then the model's probably pretty technical, or maybe it's not even that useful. So this is the idea. We like the math here, but we really want the math to mean something. If it doesn't mean anything, then we're better off just go be a math major. All right, do pure math and do it for the sake of doing math. And here in econ, we want our math to mean something. No matter how fancy it looks, it needs to represent the real world. It gets fancier because the real world is complicated. But right now, we're just starting simple. All right, we need to just be able to understand um, the like essentially the skeleton of economic models. All right. And the skeleton comes from this right here. This consumer's problem is the soul of an of economic sciences in general. So it's very important to understand the constrained consumer's problem. All right. With that in mind, let's work some examples. Okay. Here's an example of a problem that you can do only using algebra, no calculus involved. So suppose we have a representative consumer, or suppose we're considering this girl, Paula. Paula has 120 bucks to spend, and she consumes two goods, bread and water. And they say, suppose the price of bread is $5. Meanwhile, the price of water is $2. So the first thing that I might ask you to do is just simply draw the budget constraint. So this is bread, and this is water. All right. Go ahead and pause here. I'm sure you can do it, but pause this for a second and draw this budget constraint. And what you should have drawn is, at least how I recommend to do it, is mark the intercepts first. All right. So if she has income of Y equal to 120 bucks, the price of bread is $5 a piece. The price of water is $2 a piece. Then the intercepts can be recovered by just marking what is the total amount of income divided by the price of the thing. All right. So, all right, income is how much I have to spend. The price of the thing is how much does it cost me per thing. If I spend all on the income, I end up with the fraction 120 over 5 or 24. And the other way, or the other intercept rather, is going to be 120 over 2, which gives 60. All right. And then, of course, the budget line is very kind to us in that it's simply a straight line. So what can we do? We can just draw a curve that connects the two. Dang. There we go. So for part one, this is all that was needed. All right. This is the fundamental. We fundamentally need to be able to do this. All right. Now, parts 2 and 3. Let's look at part 2. Part 2 says consider some basket A, which is 4 bread and 50 waters. Now, if this is not exactly to scale, if you want to draw it to scale, then use Desmos. But maybe we have something like this. We have A, and this represents 50 waters and 5 bread. All right. Is this optimal? All right. Is this optimal? And then plot this point and draw her indifference curve at this point. I've already done one of the parts for you. All right. I've already plotted it for you. But is this optimal? Take a few seconds to think. Is this optimal? How how can I relate this rule for optimality back to a problem like this? Give yourself a few seconds to see if you might have the answer, and then I will reveal how we should be thinking about a problem like this. All right. So remember, this is an algebra problem. So no derivatives involved here. How do we do this? Well, we've been given some extra information here. All right. They tell us that Paula is willing to trade 4 waters for 1 bread here. All right. 4 waters for 1 bread here at this point. So at A, Paula is willing to trade 4 waters for 1 bread. All right. From this tells us that the slope of the IC at this point is equal to 4 over 1 or simply 4. All right. Because remember, slopes are dy dx. The slope is changing y over changing x. So what's on the y-axis is waters. What's on the x-axis is bread. And that's why we know that the slope here is 4 waters and 1 bread. So we got the slope of the IC, which is the MRS. But what about the slope of the budget constraint? All right. Well, that one's easy. I have to do no math there either. I just take the price ratio. the slope of the IC, I know that it was this, and I'm just going to put a little negative sign there, is exactly equal to 4 or negative 4. And then I need to know what is the slope of the budget constraint, the budget line. Well, I just take the price ratios, the negative of the price ratios. And here's where I will do. Here's where I will do. I do the negative of PB over P water. This is negative 5 over 2. So I know that the slope of the IC at this point is equal to negative 4. The slope of the budget constraint, the budget line at this point is equal to negative 5 halves. Are these two things equal? No. No, they are not. All right. We see that the budget, the IC, excuse me, we see that the slope of the indifference curve is negative 4. Meanwhile, the slope of the budget constraint is a negative 2.5. So here, the marginal value is greater than the marginal value of bread is greater than the marginal cost of bread, thus not optimal. This is not optimal. Paula would want more bread. One thing that I think I should have pointed out, and I'm going to point out, is why, and you might have this question right here, like, why did he do, let me show. You might be asking yourself this when I was solving this. Why did he do water on top for the IC, but bread on top for the budget constraint? Well, remember, the MRS is equal to the marginal utility of the X good divided by the marginal utility of the Y good. This, we remember that marginal utility is du dx for X and it's du dy for Y. This is the same thing. If you're a physics, if you ever took a physics class, then this is fine. If you're an applied math major, then you'll know what I'm about to do. This is fine. Um, this is the same thing as du dx times, remember, to divide by a fraction means to multiply by its reciprocal. So we have dy over du since we were dividing by this guy. These will cancel. And that's why for the MRS, we have dy dx. Meanwhile, over here, for the slope of the budget constraint, it's much, much simpler. I don't have to take a derivative. I simply see that to get the slope of this downward, to get the magnitude of the slope of this downward sloping line, I just take um, the price ratio. I simply do um, the the negative, the negative of the price ratio. And that's why the MRS is Y variable on top, but the budget constraint is the X variable on top. It might be good to write that part down just to encode it in your memory. MRS will be dy dx, meanwhile MRT will be not dx dy, but it will be the reverse. All right. And then I'm going to take advantage of good notes here. And remember, I asked you to plot this point. So we're going to paste, not that. That is not what I wanted. It's a Dropbox link to a very mathematical economics thing. So I mean, if that's what you want, you can have that. What I think we want is um let me just copy this. They used to make it so easy. Used to make it so easy to copy in the Good Notes 5, but now we're on Good Notes 6. All right. Um, I might need to create a new page, but that's all right. Okay. So let's paste this here. All right. So I've plotted the point, and I know it's not optimal, but what does this look like? It doesn't have to be a two scale and difference curve, but one of the things that would be important here is that the marginal value, remember, the slope of the IC is -4. We associate the IC with marginal value. Meanwhile, the slope of the BC is 2.5. We associate that with marginal cost. We know that these things are not equal. We know that the marginal value is greater than the marginal cost. Thus, the indifference curve should be steeper than the budget line. That would correspond to an indifference curve that looks something maybe like this. All right. So something like this. That's how we know. That's how we know, right? This corresponds to what we just saw. The slope of the IC was like a -4. Meanwhile, the slope of the BC was a -2.5. The indifference curve has a steeper negative slope than the budget curve. They are not equal, and so we know that point A is not optimal. So this is how we would do this, an example of a problem like this mathematically. Now, I'm going to shrink these things so that I can keep it all on one page. If you're doing this on your own, you may want to make a new page of notes. Or if you're doing this on good notes like I am, then you can do this very exact thing. So did we solve problem 2? Yes. We said, is this optimal? We know that no, not optimal. We've plotted this point and we drew her IC at this point, something like that. So let's move on to question 3. All right. Question 3 tells us to now consider a different basket. Um, Basket B is 10 bread and 35 water. So let's do this. You want to redraw your graph if you're drawing by hand, or if you're working on an iPad like I am, then what you would do is you'll copy and paste, make life easier. And we say, okay, now, oops, that one. Now, that was A, but we don't care about A. Now we want to consider B, all right? 10 bread and 35 water. So we're going to go a little bit further with the bread. 10 bread and 35 water. And the question asks us, is this optimal? This is point B. Well, let's see. Since this is the non-algebra problem, we've been given the values of things. All right, we didn't have to do any calculus to get these marginal utilities. They tell us, the problem tells us that Paula, at this point, Paula is willing to trade 2.5 waters for 1 bread. So at, I don't ever use this pencil. They need to just, like, I will never use this. I don't know why I have this. Anyways, so at B, the slope of the IC is equal to, remember, 2.5 waters for 1 bread. Just erase that. Right? 2.5 waters for 1 bread. Meanwhile, the slope, you can probably see where this is going. The slope of the budget constraint is equal to negative of the price of bread. I'm sorry. Yeah. The negative of the price of bread divided by the price of water. We see that the slope of the IC is a negative 2.5, and the slope of the budget curve is also a negative 2.5. So, yes, this is optimal. Why? Because the marginal value of bread is exactly equal to the marginal cost of bread, or the MRS is equal to the MRT. All of these explanations, all of these justifications will be acceptable. All of these will get you full credit on any graded work. So we know, yes, this is optimal. And we know that since they are exactly equal, this means that this should occur at a point where the indifference curve is exactly tangent to the the budget constraint. And you can, it doesn't have to be picture perfect, but just to visually illustrate what's going down. This is optimal, all right? And this is visually what we saw about optimality earlier in this lecture. This is how you want to do a constrained consumer's problem if we have to do it by hand, all right? By hand means algebraically, all right? Now, one of the weaknesses of the algebra approach is that they just have to tell you. The problem has to tell us how much Paula is willing to trade at whatever point we're considering. They're essentially giving us the MRS and asking us, is this equal to the MRT? That's good, but not good enough. You guys are much smarter than that. So let's see how we can do the same type problem, but with calculus, okay? And often I think the calculus version is much more insightful, much more illuminating of a process to work through. All right. So let's consider a similar problem, but now let's use calculus to do it. All right. So suppose they tell you that Frank's utility function, your homie, is given by 10 times x squared times z. All right. So the price of x is $10, the price of z is $5, and his income is 150. What is his optimal consumption bundle? And then they ask you to draw the budget and plot this optimal point. This is where calculus makes things easier, okay? Because now we've got a utility function and they haven't given us MRSs. We find that out for ourselves in a way. Um, and they given us the price of the two goods and his income. All right. And then they want us to find what is the optimal consumption. How I want you guys to set up these problems is as follows. Remember what I mentioned in the syllabus lecture. The key to the calculus problems is constrained optimization. All right. Constrained optimization is the heart and soul of economics, of formal economic models. The constrained consumers problem is referred to as the utility maximization problem. Or I might refer to it as UMP for short. What this means is that we have a utility function right here. Utility function is 10 times x squared times z. So u of x and z is equal to 10 times x squared times z. What do we want to do? Well, we want to max this utility. What do we get to choose? We get to choose x and z. So we remember, I will remind us that this, and I'll write this. Let's do this and this. Whatever we're maxing, if you're a math or if you're any STEM major, then you probably know what I'm about to say. But this is the objective. This is the objective function. This is the object we wish to maximize. These guys are our choice variables. All right. These are the things that we can choose to try and maximize this thing. What's missing? The constraint. All right. Remember, two types of information compose are at minimal. These two types of information are needed to form our economic model. We've got our preferences. We must also consider the budget constraint. All right. How do we write a budget constraint here? We know Frank's income is 150. We know that the price of good X is $10. The price of good Y is $5. So the budget constraint then is that 10 times X plus 5 times Y must equal 150. All right. So for all those folks that said, when is math ever useful? This is exactly it. We use math. We do this mental calculus without thinking about it. We might not actually do calculus, but you will be surprised. For those of you that I had quite a lot of you mention that you're interested in like behavioral type stuff. Um, our minds, the human brain, is actually quite good at doing a sort of mental calculus every time we make a decision. Every time you choose to do anything at all, your brain is doing something, and you're most likely doing something because the benefit is greater than or equal to the cost. All right. But back to the math. Let's go ahead and wrap this up. Of course, this is what is referred to as the constraint. All right. So we have our constrained optimization problem. In every economic model lies a constrained optimization problem. When we're working with the consumers, then we work with the utility maximization problem. As a preview, when we work with the firms, with businesses, they don't max utility, they max profit. So the firm will have a symmetric problem called the profit maximization problem, which we will see in later lectures. Okay. But for now, we're focusing on the consumer, the demand side of things. All right. So the consumer is trying to maximize their utility by choosing the goods that they can consume according to the constraints, the budget constraint that they face. All right. And there are multiple ways that you can do this. Um, oh, I just realized I need to write not X, but Z here. There we go. There are multiple ways you can do this. You solve via one is to reduce dimensionality or replace one of the variables, or I should say substitute variables, or two, you can do what's called, you can take advantage of what's called the Lagrangian. All right. Those of you that have taken multivariable calculus, then you probably have seen this before. Those of you that have taken more higher than Math 126, then you've definitely seen this before. I'll probably use this throughout the year, but right now I'm gonna go with method one. All right. So we're gonna we're gonna use this for now. All right. But the other one has quite a lot of use. All right. Though it can be a little bit, there's some things we have to keep in mind, which I want to introduce things piece by piece. I don't want to overwhelm. All right. So the substituting variables is the easier way, but it doesn't always work. The Lagrangian always works, but it takes a little bit more math knowledge. So let's keep it chill for right now. So we're going to go with this one. All right. And so what do I mean? If you watched the syllabus lecture, then you remember what I did. If 10x plus 5z is equal to 150, then let's go ahead and replace z. All right. Then I know that 5z is equal to 150 minus 10x. And I know that z is then equal to 150 divided by 5. Or I should, let me not get ahead of myself. If 5z is equal to all of this, then if I divide both sides by 5, what do I find? I find that this is equivalent to 30 minus 2x. All right. Substitute and rewrite. Substitute and rewrite the problem. We are now just maxing by choosing x. And because I have this relationship, once I choose x, then I immediately know what z is. So now I can rewrite my objective as 10 times x squared times 30 minus 2x. Okay. Here, now it's just a calc 1, find the maximum, find the extrema problem. Okay. So let's see. Here, one thing that will make our lives easier as well for all the math majors out here, here's a question. Is this equal to this? As I have here on the screen, is the left equivalent to the right? Does the x that maxes the left also max the right? The answer is yes. All right. Because it doesn't matter whether this 10 is out in front or not. Simply scaling the function does not affect the maximum. So to make lives easier, we can just ignore the 10 because whatever maxes this function will max 10 times this function. All right. The 10 does not change things. If it were a negative number, it does. But since it's a positive number, it does not. So let's work with this one. Let's work with this one. How do we find a maximum? Take a derivative, set it equal to 0, and then check its second derivative if we get multiple max or multiple extrema. So I'm going to distribute. We have 30x squared minus 2x cubed. All right. All I did was distribute this inside and then that right there. All right. How to find the max? Take derivative and set equal to 0, or what I refer to as the first order conditions. And then this becomes 60x minus 6x squared. All right. And I want this equal to 0. All right. Well, now I have a quadratic. All right. Now I have a quadratic. And we simply solve for we know how to get the solutions of a quadratic equation. All right. Now, this is calculus-based economics, but really, this is a pre-cal problem now. All right. This is the beauty of reducing dimensionality. And I know it seems like a lot of math and numbers floating around, but really we can do all of this stuff with just pre-cal and maybe just a little bit of calculus knowledge. It's really not so tough. All right. So what x value makes 60x minus 6x squared equal to 0? Go ahead and have a go at this on your own right now. I've gotten you this far. Go ahead and try and see if you can come to the right answer. I'll give you guys a few minutes to try it, and then we will resume. So pause the video now and try this on your own and tell me what is the optimal x value. All right. So let's check and see how we did. Remember the quadratic formula, quite helpful here, that x is equal to the opposite of, let me go ahead and move this down. If I rewrite this, remember we worked with quadratic formula and we saw, sorry about that. So when we were working with quadratic formula, we saw it where we see the numbers are arranged left to right by the degree of the exponent. So let me just rewrite it like this. And then it's plus 0 equals 0. So this is ax squared plus bx plus c. The quadratic formula tells us that x is equal to the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. All right, if you're like me, or if you went to a similar school as I did, they taught you a song for this, and it's forever engraved in your head. And if not, you can go check out the song. It's pretty helpful. All right, so what does this look like here? Well, opposite of b is negative 60, plus or minus the square root of b squared, so negative 60 squared, minus 4. A is negative 6, but C is 0. All right. All over 2 times negative 6. Oops. Negative 6. Okay. So it looks big and nasty to start, but then we realize, wait a minute. Negative 60 plus or minus the square root of this all gets multiplied by 0, so this goes away. So we've got negative 60 squared all over negative 12. This is then negative 60 squared is going to be 3,600. Is the same thing as negative 60 plus or minus 60 all over negative 12. And then we get two answers, all right, because we have a plus or minus. If we do the plus, then I have negative 60 plus 60, 0 over negative 12 equals 0. Or if I did the negative 60, the minus answer, minus 60, then I get negative 120 over negative 12 equals 10. All right. So you have two answers. You have two possible answers. There are a number of different calculus techniques that you can use, or even just math techniques that you can use to determine which one is a max and which one is a min. But I will give you guys a hint that you don't often consume zero of something when you have a utility function like, sorry, like this. All right, usually you don't. How can we prove? What's a quick way to show that zero is not the optimizer for this? My clever math guys or girls, how can we show that zero, that x equals zero does not optimize this? How can we quickly tell with zero math? Well, if we plug in x equals zero, what utility do we get? 0 times 10 times z is 0. Anything times 0 is 0. So I plugged in 0, I'm going to get utility equal to 0. On the other hand, if I plug in any positive number at all, then I will get a positive number. So that's a quick, intuitive way to understand why this is not it. Let me write it like this. Not that, but this is the one. All right. So that tells us that x star is equal to 10. And because I've reduced the dimensionality of the problem, I know that z, the optimal z, is simply 30 minus 2 times x star. So z star is equal to 30 minus 2 times x star equals 30 minus 2 times 10. So z star is also equal to 10. So Frank's optimal bundle is at 10, comma 10. Let's go ahead and move this up here. And so let me use this. Frank's optimal bundle is 10, comma 10. All right. And then the only thing that the algebra problem, not the only thing, one of the big things that the algebra problem and the calculus problem have in common is that I want you to not only tell me which one is optimal, not only tell me which one is optimal, but to plot this on a graph. Remember, coming back to what was given information, he has 150 to spend. Price of X is $10. Price of Z is $5. So 10 and 5. So for X, and then let's call this one Z. Remember, price of X is $10. And if he has income Y, maybe I'll just say income equals 150. Price of X is equal to $10. Price of Z is equal to $5. Then what do? Plot your first draw the budget line, get your intercepts for the budget line, and then we want to plot the optimal point, that 10-10. All right. So the x-intercept, if I have 150 bucks to spend and I spend it all on good X, then I can afford 15 of good X. Meanwhile, if I spend it all on good Z, which costs only $5 a piece, then I can afford 30 of good Z. The budget line is simply a straight line between the two. The optimal point is going to be just roughly drawn to scale, but something like maybe, I don't know, like 10 right here and 10 right here. And I know that the indifference curve must be tangent to this point. Um, the indifference curve right here, if I was real particular, maybe I should redraw it. Nah, it's okay. It's okay. As long as you've gotten the math right, um, this is valid. I think the actual indifference curve, if I were to plot the 3D function and take the slice of the 2D function, I think it would be a bit different. Like I kind of think it would be maybe something like this part is not nearly as important as everything else I said, but it would probably be something like this. But like I said, as long as you found the optimal point using calculus and you've been able to graph this point right here, as long as you can give me all of this information, I'm not gonna give us a hard time about does your graph look picture perfect accurate. All right. So this is how we do an econ problem with calculus. This is how we do the utility maximization problem, the constrained consumers problem with calculus. It's a bit more involved, but I wanted you guys to see what does it actually look like to solve a more formal economic model. Um, be prepared to be able to do this for sure on your homework, and then maybe um, memorize the steps because this is something I want you guys to know how to solve the utility maximization problem. It's exactly that. It's a maximization problem. It's a constrained optimization problem. So be comfortable with the calculus version and be comfortable with the algebra version. All right. They represent the same type of problem. So this mostly concludes what I wanted to talk about for this lecture. This completes the introduction of the consumer's problem. This forms the basis of every other problem in economics at all. All right. It's our first formal economic model that we've seen. It forms the cornerstone of every economic model, or this is the cornerstone of economic models. So we must first understand the most basic setting before we can ever hope to extend our models to accommodate more complex and thus realistic real life scenarios. As a closing note, I just wanted to point out to you guys that these utility functions, we don't just pick random mathematical functions. We economists have um, a repertoire of utility functions that behave well, behave nicely, um, and still generate interesting and relevant results that depict things that happen in the real world. So if I'm asking you to do the calculus problems, then more than likely you're going to be working with one of these, the Cobb-Douglas or a log utility. There's also a chance you work with the quasi-linear, but I'll probably be kind to you guys and say that the calculus problems that I'll make you guys do will most likely only ever involve these two. Most likely. The problems that you can solve with algebra can use all of these. So what we've been working with today is what's known as a Cobb-Douglas utility function, or just a Cobb-Douglas function. You might also see log utility. This is also very, very common. But there are other scenarios that we've heard of. And honestly, these are scenarios or these are things that you've heard of in your principles of econ class. We have what's called perfect substitutes and perfect complements. All right. And these are the functions that we use to represent those relationships between two goods. And these would be the functions that you want to use in your model if you're trying to tell me something or tell the world something about goods that are considered substitutes or goods that are considered complements. All right. And the quasi-linear is just nice to know that it exists. As a preview, I don't know if we'll see this in this class, but this is the main thing that we saw in Econ 200 or in Principles of Micro is that you'll have a supply graph and a demand graph. How did that ever first come about, get invented? Relies on a quasi-linear utility function. I don't think we'll end up seeing that. I don't think so. Maybe if I show it to you guys, it will probably just be for like for curiosity. It would never be something I ask you to do on a test, but that's just a little bit of a look ahead of what's coming. All right. That's all I have for you guys today. Watch this lecture over. Take your time watching it. Pause, play, split it in half, whatever have you. Um, but yeah, this is our first introduction to a more formal economic model. All right. Then I'll see you guys next time. All right. See ya.